Okay, this recording is going to demonstrate the use of Ohm's law to solve for voltage and current in simple circuits and circuits that can be analyzed using the method of equivalent resistance. So if we look at this very first circuit here, we have um, about the simplest possible electric circuit. It's got a voltage source and a single resistor in it, and therefore the concept of Ohm's law, which says that the voltage is equal to the current times the resistance. V is equal to IR, classic equation of introductory physics, is directly applicable to this equation because I know the voltage that's being applied across this resistor, because everywhere on this section um, of the circuit is going to, this high portion of the circuit here is all the same voltage. That is a single piece of wire, and in circuit diagrams, the wires are assumed to be perfect. There is no resistance in them. All the resistance in a circuit is symbolized, is represented by physical resistors in the diagram, like this one. So since this is a perfect wire, no resistance, it has no voltage drop across it, which means that since the top end of the battery here is positive 10 volts, then everywhere along that bold section is positive 10 volts. The voltage drop occurs across the resistor, and then this entire small section of the diagram is all connected to the negative side of the battery, which we're considering to be 0 volts, because the battery pumps from 0 up to plus 10 volts. That means everywhere on the lower section of the circuit is 0 volts, which means the entire voltage drop from this end of the resistor to this end of the resistor must be 10 volts, because the left end of the resistor is at positive 10 volts, and the right end of the resistor, because it's connected back to the negative side of the battery, is at 0 volts. So the entire voltage drop is across this resistor, therefore it's 10 volts. So I can solve then for the current through this resistor. I would equal V over R, which would equal 10 volts divided by 30 ohms of resistance, or 1/3 of an amp is flowing in this circuit. Since this is a single branch circuit, that means that 1 amp is flowing everywhere, or 1/3 of an amp is flowing everywhere in that circuit. The only time that the current changes is when there's a branch available. Okay, so let's move on to a slightly more complicated circuit. We still have a battery, and let's this time put in 2 resistors in a row like this. When there is no branch, when there's no junction, this is considered, we call this a series combination of resistors. Since it's in series, that means I only have one path available for me. So if I come around this corner with a current I, that current flows through this resistor and it is still current I. There's no alternative path for the current to take. Therefore, the current through this second part of the resistor is still I. We have one branch, one current. It's I everywhere. So given that, let's say that we want to solve for the current in this combination and the voltage drop across each resistor. So let's put in some values. Let's go ahead and use a 10-volt battery again. And this time we'll use a 30 ohm resistor like we did before, and we'll put it in combination with a 20 ohm resistor. So what happens when you have a series combination is those resistors tend to behave like one larger resistor. The sum total of their resistance is what affects the circuit. So the rule is that a series combination of resistors, the resistance of the total, or the effective resistance, I call that equivalent resistance because that's normally what we call it. The equivalent resistance, or the total resistance, is the sum of the individual resistances. So I can think of this as a new circuit which looks like this, with a single equivalent resistance in it. So this is still 10 volts, but this is no longer the individual 20 and 30. This is now the equivalent resistance which in our case is going to be 30 ohms plus 20 ohms, the sum of those. So this is the exact same thing as having a simple circuit, 10 volts, 50 ohms. And you'll notice that we've now reduced our slightly more complicated circuit into a circuit that looks exactly like our simplest possible circuit. We can now solve this. I now know that current is equal to voltage divided by resistance using the same logic as we did above. So 50 over, oops, sorry, 10 volts over 50 ohms, or 1/5 of an amp. So we're going to have 1/5 of an amp flowing in this equivalent circuit, which means that when we step back, now if we step back to this circuit, that means that we have 1/5 of an amp flowing in this circuit. We already discussed that the current is the same everywhere, so that 1/5 amp flows through each of those resistances. So now I can do the voltage drop, still using Ohm's law. The voltage drop at any point is equal to the current times the resistance. So if a 1/5 of an amp is flowing through a 30 ohm resistor, we're getting 30 over 5 volts, or 6 volts worth of potential drop across the 30 ohm resistor. We can do the same thing for the 20 ohm resistor, which would be I times R. So 20, we'll put a 30 in there, is going to equal 1/5 amp times 20 ohms, which would equal 20 divided by 5 volts, which would equal 4 volts. You'll notice that the sum of these two is 10 volts. That's good because in this circuit I have 10 volts of available potential. If I drop 6 of it across the 30 ohm resistor, I need to drop the other 4 volts across the 20 ohm resistor, because when I get down to this point down here in the corner, I have to be at 0 volts because I'm back at the 0 volt section of the battery. So the sum total of all those drops have to add up to the available potential. So I could have gotten this 4 volt by doing a subtraction here. Either way works. Okay, let's try a slightly different variation of the same circuit. We'll still have two resistances, but I'm going to connect them together in a different way. So um, this is still my 30 ohm resistor and my 20 ohm resistor, and I'll still use my 10 volt battery. But you'll notice that this circuit has alternative paths. I can get from my battery back to my battery by going two different directions. So we have these things in this circuit now, which we call junctions. And whenever you see a junction, that means that we have an alternative path. So I look for branches here. I can see that there's a branch going around like this from junction to junction. I see a branch going from this junction to this junction, and I see a branch running around this way. So I have 3 branches, and so for each branch, there's a current. Each branch has its own current. So I'm going to label this one I1, I'm going to label this one I2, and I'm going to label this one I3. You can label them any way you want. There's no rule that says that I3 has to be the one in the middle, etc. It's your choice. And the direction that they flow is also not important, as long as you mathematically do the same thing that you've done with your arrow. So when I show current flowing down in the right-hand branch as I2, then I need to represent that positive or negatively when I'm solving a problem. Not really an issue when we are using the technique of equivalent resistance, but it is a problem when we are doing, or it is important when we're doing a different technique called Kirchhoff's laws. So I'm going to break this down into an equivalent resistance, but now I have these resistors next to each other. The top ends of the resistors are tied together and the bottom ends of the resistors are tied together. This means that the voltage drops are equivalent. So since I have two different paths, I can get from this top point to the bottom point by traveling around on this path, and that gets me from the top to the bottom. I can also travel along this path, which also gets me from the top point to the bottom point. Since those points are places in potential, locations on a circuit are locations within electric potential. That means that the amount of change of potential from the top point to the bottom point in the circuit, whether I follow the yellow path or the green path, has to be the same. Because the potentials are the same, these pieces, these two resistors, are said to be in parallel with each other. When um, when they have equal voltage drop across, then those segments are considered to be in parallel. And the rule is when the equivalent resistance is equal to the sum of the inverses of the individual resistances. This is a much more complicated situation. Here we're adding reciprocals, and the result is the reciprocal. So make sure that you don't invert this equation ahead of time. So for example, 1 over R equivalent equals 1 over R1 plus 1 over R2. Remember, mathematically, this is not equal to 1 over R equivalent equals R1 plus R2. You can't invert sums of fractions here. You have to get common denominators, add them together, and then invert. So remember, this is not an acceptable mathematical operation. So let's go ahead and look at this then. Remembering the technique of equivalent resistance is to represent that equation. So this diagram can now become the following diagram. I still have my 10-volt battery, but that parallel combination has been replaced by an equivalent resistance. Let's just go ahead and solve for what that equivalent resistance is. So 1 over R equivalent would equal 1 over 30 plus 1 over 20. There's my two resistances, 1 over 30 ohms, 1 over 20 ohms. So I would now need to get the sum of that. I can do common denominators, or I can go ahead and do it on my calculator. Here, the common denominators are going to be 60 in this case. So I can multiply this first one by 2. So I could get 2 over 60 plus 3 over 60, which would be the same as 5 over 60 is 1 over R equivalent. Therefore, R equivalent is equal to 60 over 5, which, which is equal to 12 ohms. Now you'll notice that when we were in series, when we put a 50 and a 20 together, the resistance was, or sorry, a 30 and a 20 together, the resistance was 50. Series combinations made the resistance go up. Here you'll notice that the resistance went down. The reason is that we actually gave alternate paths for the current to flow through. We gave it more room to flow, more available passage to flow. So we actually decreased the resistance here by opening up an alternative channel. This is true in parallel. You should always get a result that is smaller than the resistance of the individual resistors you placed in the combination. In series, you should always get a resistance that's higher. So that means that this is the same as a 12 ohm resistor. We now are back to our simple circuit. So I can do V equals IR. I can solve for I, which would be 10 volts divided by 12 ohms, which is equal to some value, which I will calculate here, which is 0.833 amps. I now need to go backwards a step and figure out what the individual current, or sorry, what the individual currents are in my individual branches. Now, in this particular problem, I could have done it directly because I knew the voltage across each branch. So the current in branch 3, as I drew above, would be the 10 volts dropping across the 30 ohm resistor, or 1/3 of an amp. And the current across the 20 ohm resistor would be 10 volts dropping across a 20 ohm resistor or a 1/2 amp. And you'll notice that the sum of 1/2 and 1/3, if I add those together, they add up to this 0.833. Okay, so here we've seen that the combination of resistors can be broken down in certain circumstances to represent a simpler equivalent circuit. The rules, remember, are that series combinations, the equivalent resistance is the sum of the individual resistors, and in parallel, the inverse of the equivalent resistance is equal to the sum of the inverses of the individual resistors. And that is true whether you have 3 or 10 or 20 things in series or parallel. Next time we'll show how to do more complicated circuits that have both combinations of parallel and series.